Let me talk about the TS conductor in the design of the TS conductor. We have carbon fiber in the composite, and then we have aluminum encapsulation, which serve the critical purpose of protecting the carbon fiber composite. And then we have the aluminum strand, which is really what's providing the bulk of the electrical conductivity and low resistance. The composite that we use, we do not use fiberglass. And the reason for that is because when you use fiberglass with carbon fiber, you actually rub down the properties of carbon fiber composite. For example, the modulus of the glass fiber is only 1/3 of the carbon fiber. And when you use glass fiber, you sacrifice away the modulus in the composite core. And you will have challenges when you do long span or applications where you have ice on the conductor. They're going to sag because of very limiting modulus in the composite core. We also have this aluminum encapsulation layer, which is essential to our technology because the carbon composite as made, these are so-called unidirectional composite. They do have superior fiber-dominated property, low thermal expansion, very high tensile strength, very good modulus. However, the carbon fiber composite, if we add fiberglass to it, it's going to create a situation where the properties of the composite will get compromised, especially the fiber-dominated properties, including modulus. That is important to manage sag from ice loading, wind load, or long span applications. So in our configuration, we do not have fiberglass in our composite so that we can preserve the properties of carbon fiber composite, including lightweight, high strength, high modulus, and low thermal expansion. Now, the composite material made from protrusion, which is the process that's used in making the composite core, it is a unidirectional composite, and they have been known to suffer from low compressive strengths. What do I mean by that? The compressive strengths in these composites are matrix-dominated properties. And they are relevant because when we do conductor installations, and including, the conductor is stored in the reel in a storage room, because of the bending, there are situations where the conductor, and especially the composite core, is subjected to compressive stress because of bending. The matrix-dominated compressive strength is only about 60 to 70% of the tensile strength. So these type of material, if unprotected, unmitigated, they will always suffer from compression failure. And that is what happens with the first generation advanced conductor. So in the TS conductor configuration, knowing this fundamental aspect in terms of composite material science, we purposely pre-stretch or pre-tension the carbon core in our manufacturing process, and then we preserve that pre-tension with the relatively thick layer of aluminum encapsulation. So why does that help? This is very similar, by the way, to civil engineering. You work with pre-stressed concrete, and it's the same working principle. Now, our composite core, the carbon composite core, is actually under pre-existing tension before it is spooled, before they are installed in the field. And if the lineman is bending the conductor for whatever reason, or the setups, it will have that additional robustness to accommodate extreme bendings, including sharp edge, where the sharp edge has been I would say, the most vulnerable situation for the first generation advanced conductor. And the aluminum layer, by the way, had to be sufficiently thick so that you are able to preserve the pretension. Because if they're too thin, they're going to simply just spall, and you will not be able to preserve that pre-stretching in the carbon core. And by the way, the relatively thick layer of the aluminum encapsulation helps the TS conductor to be compatible with the traditional way of doing conductor installation, maintenance, and repair. And what do I mean by that? That relatively thick layer provides the cushion so that when you do crimping for conventional conductor splicing or dead endings, for example, we can protect the carbon core from getting crushed while we're using the familiar tools, familiar equipment, familiar methodology, and familiar training by linemen who know how to work with AZSR conductor. And at the same time, the relatively thick layer is also needed because we do not want the aluminum layer to be worn out so that you can provide that effective barrier against corrosions. And on the aluminum side, the aluminum strands, we typically work with trapezoidal wire and annealed aluminum. And the reason for that is quite obvious because the annealed trapezoidal configuration for aluminum gives you maximum packing. And that maximum packing allows you to get optimal ampacity and also drive the resistance to the minimum possible. So you have a conductor that incorporates the most possible aluminum, and this conductor also does not necessarily create a weight penalty because we have taken 80% of the weight of the steel out by replacing steel with carbon composite core. So now you have a conductor that can go to high temperature to reach that high ampacity without a sagging problem because the carbon fiber composite does not have thermal expansion. And we also talked about you can pack as much aluminum in there without the weight penalty that is associated with traditional conductor. And lastly, we can use annealed aluminum that doesn't have much of a strength to contribute to the conductor, yet our conductor is actually stronger than traditional conductor because the carbon composite offers twice the strength of steel. And in addition to that, we also address the fundamental concern utility had, which is the safety, reliability, longevity, and workability aspect of conductors because of the effective protection provided by the aluminum encapsulation.